Welcome back to the video series on integration and differential equations. In today's video, we're going to take a look at the bad case. We're going to be doing a second example of a non-homogeneous DE with constant coefficients. And we're going to talk about this bad case. We'll discuss what the bad case is and how we handle it. If a term appears in both yc and yp, we'll multiply the term in yp by the smallest power of x that avoids a repeat. So the bad case is this situation where a term appears in both yc and yp, and what we do about it, we will fix up any term or terms in yp that are having this problem, that are repeated in yc. Here's the DE that we're going to be solving today, and we're going to run through the same 5 steps as we outlined in our previous video. So step 1 is to find the complementary solution, yc. To find yc, we are going to set the right side of the DE equal to 0, and we're going to set up the auxiliary equation in the usual way. So the y double prime becomes m squared, and the rest of our equation looks like minus 4m plus 4 equals 0. Now we can solve this equation here either by factoring or by the quadratic formula. So I would suggest we factor. That's a perfect square. M minus 2 all squared is equal to 0, which tells us our solutions are m equal 2 and 2. So we're in the situation of repeated real roots. Right, so with that we can write down our yc, our complementary solution, and our initial thought on what that looks like. We would probably write down c1 plus c2x times e to the 2x. So that's the formula for dealing with repeated real roots. Okay, so a couple of comments about this. First of all, let's make sure to call this yc. We would not want to call it y. We're reserving the symbol y for the general solution at the end of the problem. So we have not found y yet. This is just yc at this point. Second thing that I would point out, this will be useful in the second step. We might actually want to re-express yc. So let's actually expand this out here, and we'd have c1 e to the 2x plus c2x e to the 2x. Step 2, we're going to set up yp, our particular solution. To set up yp, we'll want to look back at what function we had on the right side of the DE. So in this case, our function of x is 12 plus 2 e to the 2x, and usually we give that the name f of x. So f of x is whatever function of x you've got on the right side of the DE. Okay, now we need to think about what sorts of terms are going to come up both in f of x and in the derivatives of f of x. So let's take a couple derivatives here, say f prime of x, f double prime of x, and see what's going on. So in our first derivative, the 12 disappears, and we get 4 e to the 2x. Okay, we've got a factor of 2 coming down in front when we differentiate that exponential e to the 2x. So we get 4 e to the 2x for our first derivative and 8 e to the 2x for our second derivative. Okay, and we could imagine continuing to take derivatives here, and all we would get is just terms that look like e to the 2x with various coefficients. So as we look at all these different terms here that we've generated, both in f of x and in the derivatives, there's only 2 types of terms that we're running into. There's a constant, and other than that, there are these exponential terms. So two types of like terms. All right, so the way that we're going to express yp is we want yp to represent these two different types of like terms, but we want yp to have unknown coefficients. So we would write something like capital A being our first unknown coefficient times 1, so that's just representing the constant, and then plus b, another unknown coefficient, times the exponential. Okay, and maybe an even simpler way of thinking about this is that the first term would just simplify to a, so it's not necessary to write a times 1. So you could just think of that a there as representing your constant. So we've got a constant term and we've got an exponential term. And most important thing here is that we've got these unknown constants in here, unknown constants a and b. So if we had more terms in here, we would call our unknown constants c, d, e for those different coefficients of our different like terms. Okay, so that's how we handled yp in our previous example. But now we are starting to realize that this is incomplete. So what we actually need to do here is put a question mark and ask ourselves, is this correct? So let's revisit our discussion up here about the bad case. So if a term appears in both yc and yp, this is the bad case, and what we need to do is multiply the term in yp, the problematic term in yp, by the smallest power of x that avoids a repeat. So let's take a look at yc here, and let's compare it to yp. And notice that we're using the expanded version of yc just so that we can clearly see what types of terms we've got. So yc has an e to the 2x term, and it has an x e to the 2x term. Okay, and then what does yp have at this point? It's got a constant, and it's got an e to the 2x term. Okay, so we've got a problem. See, this e to the 2x, that's repeated up here. So you could say this is the bad case. This particular term here, this second term, is a problem. The a is fine. So we're going to adjust yp on a term-by-term basis. We're going to say a is fine, no change required, but we're going to have to deal with this second term here. Okay, so what do? We multiplied the problematic term in yp by the smallest power of x that avoids a repeat. So we could ask ourselves, is multiplying by x going to be good enough? Is x e to the 2x already used up here in yc? Yeah, unfortunately it is. X e to the 2x also appears in yc. So multiplying this term here by x isn't going to be good enough, but if we multiply by x squared, that's fine. There's no term x squared e to the 2x in yc, so we've managed to avoid a repeat. All right, so we've now had a comprehensive discussion of how to set up yp. We saw in the first video the basic idea of setting up our function, taking derivatives of that function, and then figuring out what sorts of like terms appear. We know that we're going to use these unknown coefficients, a and b, when we're representing those like terms. And we now know, we've had our discussion of the bad case, so we know that we always need to check for the bad case and modify any terms that are problems. So there we go, we've got our yp. So we're now done the first two steps of the problem. I've recopied the question itself, and I've recopied our yc and our yp from the first two steps. So now for step 3, we're going to plug yp into the DE, and this is where we're going to find these unknown coefficients. So in this case, we'll find a and b.